Welcome. This is the bonus week, part one of the Electrical Code Coach training program. What is the permitted reduction for some neutral conductors for service or feeder loads? So it's asking about neutral conductors, and it's going to be about services or feeders. So let's use our keyword and index process. I would say that the overall theme of this question would be neutral or neutral conductors. So let's try N for neutral in our index. Why don't you pause the video now and see if there is N for neutral in the index. Okay, so when we get to page 855 in the index, in the third column over, up toward the top, we do find that there is a neutral section. Now, what do you think the next keyword we should use is? Let's see if we can find something about services or feeders. So let's look down through there. Okay. As we look down through, about a quarter of the way down, we find feeder and service loads. And it's got several articles listed here. The first one is listed is 220.61. Let's head there first. Pause the video now if you need to. Okay, when we get to page 73 of our 2017 NEC Codebook, you're going to find 220.61. It says feeder or service neutral load. So the basic calculation for feeder service neutral load shall be the maximum unbalance of the load determined by this article. The maximum unbalanced load shall be the maximum net calculated load between the neutral conductor and any one of the ungrounded conductors. So there's going to be some parameters here. We've got some questions here in this bonus lesson, and it's going to teach you, the basic principles of it. So let's go ahead and flip over to page 75. You can kind of get lost here if you don't know what you're looking for because they have some other tables in between. But when you go to page 75 and you look just under the dryer or the demand factor table for kitchen equipment, you're going to see B, permitted reductions. Now that is actually 220.61 just continued over to here. So part A was the general description. Part B is going to be the permitted reductions, and that's what we're dealing with today. So a feeder or service supplying the following load shall be permitted to have an additional demand factor of 70% applied to the amount that is in parts 1 and 2 here. And we're going to learn about that now. So part 1 says a feeder or service supplying household electric ranges, wall-mounted oven, counter-mounted cooking units, and electric dryers where the maximum unbalanced load has been determined according to our dryer table, table 220.55, or excuse me, that would be our range table, or to table 220.54 for dryers. So as long as you have figured out your load according to table 220.55 or 220.54 for dryers and ranges, that portion of that, if you were doing a whole house load calculation, can have a 70% reduction on its load. And don't worry about that too much. We're going to spend a couple questions looking on how to calculate this, okay? So, but what it's saying is for ranges and dryers, you're allowed to take a 70% reduction when sizing the feeder conductors or service conductors for loads that handle the dryer and the range. And we'll explain it. Part 2 says the portion of the unbalanced load in excess of 200 amperes, where the feeder or service is supplied from a 3-wire DC or a single-phase AC or a 4-wire 3-phase system, which would be, it's going to be a Y, and then and it could be delta as well. It doesn't specify here, so either one, or a 3-wire 2-phase system or a 5-wire 2-way system. So if you had a normal 4-wire 3-phase system or a 3-wire 2-phase system or a 5-wire 2-phase system, you could do a 70% reduction on any of the neutral current that is above 200 amps. And I have a practice question in this lesson for that too. So let's move on. So we read and we recapped the permitted reduction for some neutral conductors or service feeder loads is 70%. It's a 70% reduction. So let's go on and learn about it. What is the calculated neutral load for a 1,500 square foot home with an 1100 watt dishwasher, a 9 kW range, a 35 watt water heater, and a 5 kW dryer on a 122 40 volt service. I'm putting in here that the loads are calculated using the standard method. Okay, so first we're going to figure out our VAs per square foot. We've learned this already. This is our basic load calculation. If you are catching this in the middle, I have an entire 10-week free course that teaches you how to do all the things leading up to this. It's absolutely free. Would love for you to check it out. So we have 1,500 square foot multiplied by 3 VAs per square foot. That's going to give us 4,500 square foot VAs. Now we have to remember our small appliance and laundry circuits. So that's going to be 2 small appliance and 1 large laundry circuit. Both of those are calculated at 1,500 each. That's going to give us 4,500 VAs for those. That's going to give us 9,000 VAs. Now we need to do our demand factors for the first portion of our load calculation. So step 1, we have the first 3,000 at 100%. Step 2, we do the next 301 up to 120,000 at 35%, which is going to allow you to do another 117,000 total at this 35%. And then step 3, we're going to add those back together. Okay, so we take 9,000 for step 1. We're going to minus the 3,000 that we need to do at 100%. That's going to give us 6,000. Now we take that remaining 6,000, we're going to multiply that by 0.35, and that's going to give us 2,100 VAs. Now we need to add those back together. We take 3,000 and we add 2,100, and that's going to give us 5,100 total general square foot and small appliance laundry circuit VAs for this load calculation. All right, now that we've done our demand factors, we need to go back and recalculate our load. So essentially we're going to calculate all of the 110 loads, and we are going to do a reduction on the dryer and the range because of the nature of the device and its neutral current. So our general square foot VAs were 5,100. Our dishwasher is 1,200. Our water heater is 0. It's a straight 240 appliance. Our range is going to be, we're going to go to table 220.55, and our range in our calculation was 9, but we are going to select from column C, and everyone in between 8 and 12 is going to be 8 kVA. And we learned about that in a previous lesson if you haven't learned all about range calculations. But now we get to take that 8,000 and do a 70% reduction on the neutral load. So we can take 8 multiplied by 0.70, and that is going to give us 5,600. Now we take our dryer and we do the same thing. We know that with the standard method, it is a minimum of 5,000 or the nameplate. In our question, it was 5,000, so we just use 5,000 multiplied by 0.70. That's going to give us the neutral calculated load of 3,500 VAs. So we're going to total those all together, and then we're going to divide by 240. So we're going to use basic Ohm's law, what we've learned before. We're trying to achieve amperage, so we divide our watts, which is our VAs. We're going to divide that by the system voltage, which is 240 in this case, and that is going to give us 64.1666. You're going to round down to 64 amps total for your neutral connected load. What is the final calculated neutral load for a service with a calculated neutral load of 230 amps on a 3-wire AC service? Okay, so we're going to head straight to 220.61 again in part B, and it lets us know that if it is in excess of 200 amps, the portion of the neutral calculated load that is in excess, that is above 200 amps, that portion can have a 70% reduction. Okay, so in this question, our neutral load has been calculated for us. It's 230 total. We can apply a 70% reduction to the portion that is beyond 200 amps. So we take 30 multiplied by 0.70. That's going to give us 21 amps. Now we have to add back the 200 because it's our base. So 200 plus 21, our reduced load, is going to equal a calculated neutral load of 221 amps. I do want to note that now you would size your wire based off this amperage. Same thing in the last question. you would go size your wire based off of 64 amps. So if you know the neutral calculated load and you can do all the reductions, you can actually size your wire based on that when you're doing your sizing. But this will be your new ampacity that you would size your wire by, and this is going to be 221 amps for this calculation. What is the minimum AWG size feeder tap conductor allowed on a 10-foot tap with a circuit that leaves the enclosure with 3-aught copper conductors on a 200 amp main overcurrent device terminating to 75 degree C terminals? So there's a lot going on here. Let's use our keyword and index process and break it down. So let's try F for feeder tap conductors. If you look at the overall theme of this question, it's asking about feeder tap conductors. It's asking about size, and it's got some different, it's got some different information in there for us that might lead us in the right direction. So, okay, so let's head to F. Let's go ahead and pause the video now. I want you to head to F in the index, and I want you to look for feeder tap conductor. Okay, so when we get to F in the index, we do find feeders. We do not find feeder tap conductor specifically, but now we're in feeders. We feel like we're in the right section. We're on page 838 in the third column. Up at the top, we see feeders. Now let's look down in alphabetical order and see if we can find anything about taps. So we go down through. We skim through till we get to the T, and we do find taps. So we found feeder and taps. So we feel like we're in the right section. Lists a bunch of different articles. Let's just go ahead and go through them in order. First, let's try 240.21b. Remember, keep a piece of paper or your hand in the back of the index just in case you need to flip back. Pause the video now and head to 240.21b. Okay, so when we get over here on page 96, in the bottom left-hand corner, we're going to find 240.21, and then we find B, and it says feeder taps. So I feel like we're in the right section. Let's go ahead and continue to read. Conductors shall be permitted to be tapped without overcurrent protection at the tap to a feeder as specified in 240.21 B 1 through 5. Okay, so it's going to talk about a bunch of different type of tap conductors. We're looking now, we need to go through our keyword and index process, and we need to look for something that is about 10 feet because, we have to go back to our question. We're trying to find out. Okay, so in this case, allowed on a 10-foot tap with a circuit that leaves the enclosure. So we've got a little bit of information. So we look at the black bold headings until we find something about 10 feet long. All right, so now that we've caught up to this point where you look at our black bold headings, we see that right here in part 1, it's for taps not over 10 foot long. If the length of the tap conductor does not exceed 10 foot and the tap conductors apply with all of the following. So when the code book says all of the following, that means it's got to hit every point. We're going to briefly go over it, and then I'm going to take us down to our section. But if you were going through this for the first time, you might want to read every single one of these sections to the T as you're looking for your answer. So the ampacity of the tap conductor is A, not less than the combined calculated load on the circuit supplied by the tap conductor. So if you know that you're tapping this conductor for a 30 amp motor, regardless of all these other codes, it has to be, the wire has to be sized for the 30 amp motor. So, okay. Part B says not less than the rating of the equipment containing an overcurrent device supplied by the tap conductor. So by the rating of the equipment. 2 says the tap conductor does not extend beyond the switch or panel board. Part 3 says except at the point of the connection to the feeder, the tap conductors are enclosed in a raceway or a switchboard or panel board or control device. And then if part 4 is what we're looking for in our question. For field installations, if the tap conductor leaves the enclosure or vault which it is made, the ampacity of the tap conductor is not less than 1/10 of the rating of the overcurrent device protecting the feeder conductors. Okay, so in this case, we're going to use part 4. because our question states that the conductors leave the enclosure, okay, and it lets us know that it is on a 200 amp main overcurrent device. So in this case, our conductors, regardless of the load, even if you have a 2 amp load, you have to size this thing, if it leaves the enclosure, at a minimum of 1/10 of the overcurrent device that you're tapping from. So we're going to do some simple math, and this is all going to make sense, and we have one more practice question after this. Okay, so we're going to take our main overcurrent protective device, and we need to divide that by 10, because we have to do at least 1/10 of it. So we're going to divide by 10. That's going to give us 10 equal portions of the 200 amps. So in this case, 20 amps is what we now can size our wire by minimum. So even if you only have a 3 amp load and you know the load, you can do a minimum of 20 amps, and that's what you must size your wire by. Now, we are going to head to our ampacity table using our ampacity tab, and that is table 310.15b16. Go ahead and flip there now. So we use our ampacity tab. We're going to flip to page 150. We're dealing with copper conductors, and we are going to go to the 75 degree C column, and we're going to go down and we're going to size based off of our amperage, and that is going to be a 14 gauge wire in this case. So for this tap conductor, you are allowed to use a 14 gauge wire being protected on a 200 amp main breaker. So I know it sounds crazy, but this is how tap conductors work. And hold on, we're going to do another question. What is the minimum AWG size copper feeder tap conductor allowed on a 25-foot tap with a circuit with 3-aught copper conductors on a 200 amp main overcurrent device with 75 degree C terminals? So we're going to use our keyword and index process. We're going to try F for feeder tap conductors. And what do we find? So close your book, go through the motions again, go to F, and see what you can find. Okay, so we use our keyword and index process. We do find feeders in the index. Then we're going to look for something about taps or tap conductors. So we go down, we find taps. It sends us over to 240.21b. When you head over there on page 96, you're going to want to make sure you feel like you're in the right section. Part B is dealing with feeder taps. That's exactly what we're dealing with. Now we're going to look at our black bold headings until we find something about 25 foot long. Make sure you always go in order from left to right, looking at the black bold headings, because if you look down here in part 2 on page 96, it says taps not over 25 foot long. If you look at part 3, it says you might see 25 foot long, but if you look up there, that is for taps supplying transformer conductors. So you have to be very careful. Always read in order, because we're going to come to part 1, it says taps 10 foot long. You come to part 2, it says taps 25 foot long. But if you're not careful, the one right under that says 25 foot long, and if you look on the next page in part 4, it says 25 foot long. So always go in order from left to right. When we find part 2, it's what we need. So where the length of the tap conductor does not exceed 25 foot, and the tap conductor applies with all of the following. Now, the longer the tap in this case, it's going to be less stringent, but it's also, in as far as how many points it does have to hit, but it's also not as lenient with the ampacity, and you'll see what I mean here in a minute. So part 1 says the ampacity of the tap conductor is not less than 1/3 of the rating of the overcurrent protective device. The tap conductors terminate on a single breaker or a single set of fuses that limit the load ampacity of the tap conductor, meaning that it's going to land to a device that is going to limit it from that point out. So in between there and there, theoretically, it should never pull more than that overcurrent protective device allows. The tap conductors are protected from physical damage, and that's going to be a given in any electrical installation. So our question states that we have a tap 25 foot long and a 200 amp main overcurrent device. So really the only thing we have to make sure we hit for our question is that we need to find 1/3 of the rating of the overcurrent protective device. Okay? So we're going to take our 200 amp OCPD. We're going to divide that by 3. We just need to find what 1/3 of it is. We divide by 3. We find that 6.66 amps is what we're going to size our wire by. What you're looking for is your new allowable ampacity. So we are going to, or the ampacity that you're going to size your wire by. So we're going to head over to our ampacity table on page 150, table 310.15B16. We're going to use the copper column, and we're going to use the 75 degree C column because our question states that it's 75 degree C terminals. So when we get over there, we're going to look down. We need to size it for a 67 amp load. And we're going to go down and find out that number 6 is only good for 65. So we're going to have to go to the next size up, which is going to be a number 4 conductor that is good for 85 amps. Okay, let's learn how to do voltage drop calculations with 3-phase. So it's very similar. You just change one of the values, and it's going to be because of the nature of 3-phase. We're not going to get too far into the nature of 3-phase and its calculations. I'm just going to teach you how to do it and what numbers you need to change to get a correct answer when you're dealing with 3-phase voltage drop. So our normal voltage drop calculation is voltage drop equals 2 kid over C mils. So it's 2 multiplied by the constant value, K value for copper or aluminum, depending on which one you're using. I is going to be current, D is distance, and the circular mils of the wire you're going to divide up into that value. So first you're going to plug in everything that you already know. 2 in our formula is a constant when dealing with single phase. When you're dealing with 3-phase, that new constant is going to be 1.732. So you're going to substitute the 2 for 1.732 anytime you're dealing with 3-phase voltage drop calculations. So you have 1.732 multiplied by our K value for copper, which we know is 12.9. You're going to multiply that by 200, which is the amperage, and then you're going to multiply that by the distance, which is 225 feet in this case. Then you need to divide that number by the circular mils of, in this case, it looks like it's a 4-aught copper conductor. So to find that out, we're going to head to Chapter 9, Table 8. Pause the video now. Use your tabs, and you can head to Chapter 9, Table 8. It says Conductor Properties, Chapter 9, Table 8. Go ahead and head there now and see if you can find the circular mils of 4-aught copper. And when we get there, we're going to find that the C mils are 211,600, 211,600. So we are going to put that back into our formula, and we just do the math. So we multiply 1.732 by 12.9 by 200 by 225. Then we're going to divide that by 211,600. And that is going to give us a voltage drop of 4.75. So it's very similar to the voltage drop for single phase, but when you're using 3-phase, because of the nature of how it breaks down, it is going to be 1.732. I may make some videos later, and there's lots of great stuff on the web going into deep into the dynamics of 3-phase and how you read across each point and why. But today we're just getting into test prep, so we can get into that some other time. What is the voltage drop of a 200 amp circuit using 4-aught aluminum conductors that is 225 foot long on a 12208 system? So we have to be very careful here that we read our question carefully. So we have aluminum conductors and we're on a 3-phase system. So let's go ahead and proceed with what we know. This is our normal voltage drop formula, 2 kid over C mils. And with 3-phase, we have a little bit different step. So first we're going to plug in everything we already know. Remember, when we're dealing with 3-phase, we must use 1.732 as our constant and not 2. Then we're going to multiply that by the K value for aluminum. So we have to be really careful here. The K value for copper is 12.9. The K value for aluminum is 21.2. The first thing I do when I get in the testing center, when I take a test, is I will get a scratch piece of paper. Listen, they won't let you take notes in, but once you get in there, you can write down whatever you want. So the first thing I do when I get in there is I get a scratch piece of paper and I write down 2 kg/C mils. I write down 12.9 for copper. I write down 21.2 for aluminum. And I write down 1.732 for all my three-phase questions. If you've got those keys, you can answer tons of questions that might come your way. So continuing with our voltage drop calculation, 1.732 multiplied by 21.2 multiplied by 200 multiplied by 225. Now we're going to head to Chapter 9, Table 8 to figure out our C mils for 4-aught. 4-aught is going to be the same regardless of copper or aluminum. Its circular mils is going to be 211600. And we're going to type in everything that we know. We're going to type in all the top line information. Then we're going to divide that by 211600. That is going to give us a voltage drop of 7.8, which is going to be over the NEC recommendation of 5% for the entire feeder. So this is going to be, you're going to have to upsize your wire probably to 250 or higher. So that's how you do the three-phase voltage drop calculations. Now let's do a three-phase whole service calculation. What is the total calculated demand in amps for a 1,600 square foot home with the following loads on a 12208 service? So you have the garbage disposal, dishwasher, water heater, dryer, range, heating, cooling, and we have some options here. So you're going to treat this like a normal calculation. We're doing the standard method in this calculation, and then we need to figure out what the actual amp draw is on a 12208 volt service. We're going to do a little bit different with our calculation at the end to figure that out than we would from a normal single phase. Step 1, you always figure your general square foot and your small appliance laundry VAs. First, you're going to calculate your general square foot VAs. 1,600 square foot multiplied by 3 is going to give you 4,800 square foot VAs. Then you're going to add your 4,500 VAs for your small appliance and your laundry circuits. I cover load calculations in depth in the free 10-week course. If you've not studied that, go back, take the whole course. It's absolutely free. Then you're just going to add those two together. You take your general square foot VAs and you add those together with your small appliance and laundry circuit VAs, which is going to give you a 9,300 total. Okay, so you take that total. Now we must apply demand factors to this portion of the calculation. Table 220.42. We take our first 3,000 VAs at 100%. So in step 1, we take our 9,300 total. We're going to minus 3,000, and we are going to get 6,300. We're setting those 3,000 to the side. In step 2, we're going to take our next 3,001 up to another 117,000 at 35%. So we're going to take 6,300, multiply it by 0.35, and that is going to give us 2,205 VAs. Then we need to add those back together. So we take the 3,000 that we set aside because it must be calculated at 100%. We're going to add that together with the 2,205, and that is going to give us 5,205 VAs. Okay, so we set that there. Now we need to go to our fixed appliances. Now the fixed appliances. When you're doing the standard method, you are going to apply the standard method rules. In this case, there are not more than 4, so our 4 or more 75% rule does not apply. In this case, since there's only 3, you're just going to total them together. Okay? That is going to give us another 5,500 VAs. Now let's head to our dryer. Okay, so our dryer is 4,800 VAs. We know that when using the standard method, you must use a minimum of 5,000 VAs or the nameplate, whichever is greater. So we're going to use 5,000. Now let's do our range. Okay, in this case, our range is 11,000. That is going to fall in column C of table 220.55. And we're going to use one range, and that is calculated at 8 kW. Now we're going to do the heating or cooling. All right, in step 5, we need to select the larger of the heating or cooling. We have heating at 10 kW, and we have cooling at 18 amps divided by 208 volts. We can just do 208 straight out because it's just line to line. And we are going to end up with the heating being the larger one. Now we need to just add it all together. So we have our general, fixed appliances, dryer, range, and heating. That is going to equal 33,705 total VAs. Now, if this were a 120, 240 volt service, we would just divide 3,705 divided by 240, and we're going to get 100 amps. But to size a service for three-phase, there's one extra step to the calculation, and it's very important. And it goes back to the 1.732 that we learned because of the nature of three-phase. You must take the square root of 3, which is going to give you 1.732. We're not going to get into the technicality of that right now, but we can learn about it at a later time, or you can self-study on that. Today we're focusing only on testing. So what you're going to do is you are going to take your 33,705 VAs and you're going to divide it by your system voltage multiplied by 1.732. So first you must take 208 multiplied by 1.732, write that down, then divide 3,705 by that number, it's 360 approximately, and that is going to give you 93.625. You're going to round up to 94 amps, and that's what you would size your service by. Obviously, you'd size your wire according to the amperage load, make sure it covers it at a minimum, and then you're going to select a standard ampere breaker rating from 240.6A. So thank you for joining me for the bonus content. We're going to have a week 2 of the bonus content, and we will see you guys soon.